In 1995, the Hubble Space Telescope brought humanity a breathtaking picture of the universe. From the data it collected, scientists estimated that the universe contains approximately 100 to 170 billion galaxies, a number seemingly insurmountable. But that's only what lies within our view, within the range that light can reach Earth, called the Observable Universe. Beyond that boundary, there remain countless galaxies that Hubble cannot yet reach. Many astronomers believe that what we see is only a small part of the true picture, perhaps less than 10% of the total number of galaxies in the entire universe. Thanks to more modern research and equipment today, that estimate has been raised to nearly 2 trillion galaxies, dozens of times the original figure. Yet even that enormous number is still just a small slice in the infinite ocean of the universe. How vast is the universe? How fast is space expanding? These remain colossal questions that leave all of humanity awestruck. Light, the fastest thing in the universe, travels at nearly 300,000 kilometers per second. And according to Einstein's theory of relativity, nothing can exceed that limit. However, the very space that light travels through refuses to sit still. It continuously expands, and this expansion causes distant galaxies to be pushed away from us faster than light itself. This doesn't violate the laws of physics, because it's space itself that's stretching, not the galaxies flying faster than the speed of light on their own. The result is that light from the most distant regions of the universe will never reach Earth, because the distance between us and them is increasing faster than the speed at which light can close the gap. So how large is the universe really? Can light truly be left behind in the race with expanding space? The answer may not completely satisfy your curiosity, but it will certainly help us grasp something of the unimaginable vastness of the universe, a place where even light becomes sluggish. Since Nicolaus Copernicus put forth the argument that Earth is not the center of the solar system, humanity has entered a revolution in perception. Our view of the universe completely changed from a small world revolving around humans to a vast universe where we are but dust amid infinity. Over centuries, new discoveries have continuously been added, but instead of making the universe easier to understand, they've made it more magnificent and mysterious than ever. The question, how truly vast is the universe, has echoed through every era, driving scientists to relentlessly seek answers. But how can we measure the size of something that the naked eye cannot fully see? It took hundreds of years of progress, from the first telescopes to modern space observation equipment, for humans to gradually determine the true scale of the universe with ever-increasing accuracy and reliability. Today, humans can measure the distance between planets using an extremely precise method, sending radio waves to them and measuring the time it takes for the signal to reflect back. This method helps us determine distance with very small margins of error, but it's only effective within the solar system, with relatively nearby planets like Venus or Mars. One of the famous tools that performed this technique was the Arecibo telescope in Puerto Rico. Before its collapse in 2020, it not only measured distances but also mapped the detailed shapes of asteroids passing by Earth by analyzing radio waves reflected from their surfaces. However, when wanting to measure distances to stars, humans must use the parallax method. Its principle is quite simple. Observe the same star from 2 different positions in Earth's orbit, 6 months apart. Then calculate the very small angular shift that the star creates in the sky. Based on that angular shift and the diameter of Earth's orbit, we can determine the distance to the target star. Many people have wondered, if the sun and stars are all moving, how can this measurement be accurate? The answer lies in the fact that everything in the Milky Way, from the sun, the planets to distant stars, is moving together like a unified system. Therefore, although the universe is always in motion, the relative motion between us and the stars remains stable enough to perform extremely accurate measurements. Thanks to this, parallax measurement remains the most accurate tool for determining distances to stars within approximately 100 light-years. However, When going beyond that limit, the angular shift becomes too small, and Earth's orbital diameter is too small to yield reliable results. To measure greater distances, astronomers turn to a more sophisticated technique, main sequence fitting. They measure the brightness and color of a star, thereby determining its type and age, then compare it with similar stars near Earth. Stars whose distances have been determined by parallax. Because stars in the same main sequence have similar mass and intrinsic brightness, if a star of the same type appears dimmer, it means it's farther away. These stars are called standard candles, natural beacons that help humans measure the depth of the universe, step by step drawing a map of infinite space. In 1908, astronomer Henrietta Swan Leavitt at Harvard University discovered a special type of variable star called Cepheids. She noticed that the period of brightness oscillation of these stars is directly proportional to their true brightness. And from this, humans could calculate distances to distant galaxies simply by measuring the brightness observed from Earth. This discovery opened one of the greatest breakthroughs in the history of astronomy, helping us measure the true scale of the universe for the first time. Besides Cepheid stars, scientists also use Type 1a supernovae explosions, extremely bright events with very stable brightness, to determine distances between galaxies. These explosions function as cosmic standard candles, helping to extend the measurement scale beyond billions of light years. However, the problem lies in this. Type 1a supernovae are very rare and unpredictable. We cannot continuously observe hundreds of billions of galaxies just waiting for an explosion to appear. Therefore, despite being a powerful tool, this method still depends heavily on luck, and humans are still striving to find more stable cosmic beacons to measure even greater distances. In 1920, astronomer Edwin Hubble made a discovery that completely changed humanity's perception. Light from distant galaxies was stretched, gradually shifting toward the red end of the spectrum. This phenomenon, called redshift, showed that galaxies are moving away from us, and therefore the universe is expanding. Moreover, Hubble realized that the farther the galaxy, the greater its recession velocity, a magnificent discovery that gave birth to the expanding universe model, completely changing how humans perceive space and time. Today, the most ancient light we can observe is the cosmic microwave background, the remnant of the Big Bang, born when the universe was only about 380,000 years old. Data from the Wilkinson Microwave Anisotropy Probe satellite and subsequent observations show that the cosmic microwave background radiation is currently about 46.5 billion light-years away from Earth. This means that in every direction, the farthest boundary humans can see, called the Observable Universe, has a radius of 46.5 billion light-years, equivalent to a diameter of about 93 billion light-years. It's hard to believe that a universe only 13.8 billion years old has such enormous dimensions. The reason lies in the fact that space itself is expanding exponentially, causing galaxies to be swept away from each other faster than the speed of light, while still not violating any laws of physics. According to precise measurements from the Hubble telescope, the current expansion rate of the universe is 73 kilometers per second per megaparsec. 1 megaparsec equals 3.26 million light-years. This means that for every 3.26 million light-years of distance, two galaxies will move apart by an additional 73 kilometers per second. In the most distant regions of the universe, this speed can reach more than 6 times the speed of light, not because the galaxies themselves are moving that fast, but because the space between them is expanding faster than light can traverse. In about 10 billion years, the universe will expand to double its current size. And if after 13 billion years, some new civilization emerges in our local galaxy cluster, then the entire universe they see will consist only of that galaxy cluster. All other regions of space will have moved beyond observation, pushed so far away that their light can never reach them. Oxford philosopher Nick Bostrom introduced a chilling concept known as the Great Filter. It suggests that most life inevitably runs into an evolutionary barrier that is nearly impossible to overcome. Maybe it's the leap from non-living matter to life. Maybe it's the jump from single-celled to multicellular organisms. Or maybe it's a step humanity has yet to face. If the great filter lies ahead of us, then most civilizations, according to astronomers' estimates, the actual universe could be 250 times larger in volume than the currently observable universe. This means the part we're seeing is like a speck of dust in an infinite ocean. And remember, we're living when the universe is nearly 14 billion years old. During that time, most of the universe has expanded so far that it can no longer be observed. In human imagination, the universe is often visualized as a giant sphere, because from Earth, we can see in all directions with nearly equal distances. But recent observations from the Planck telescope show that the universe on a large scale is almost flat, meaning it has no significant curvature. This doesn't mean the universe is truly flat like a sheet of paper, but rather that the part of space we can see is so small compared to the whole that it appears flat, similar to when you stand on Earth and don't notice the curvature of the planet you're living on. With the ever-increasing expansion rate of the universe and the mysterious presence of dark energy, up to 97% of the observable universe will forever remain beyond human reach, even if we began traveling at the speed of light from this very moment. It sounds paradoxical, but that's exactly how it is. Even moving as fast as light, we could only reach about 3% of the universe's volume, because space continuously expands, stretching every destination farther away before we can get there. Dark energy is what's driving that expansion. It causes space to expand more and more, but doesn't change the nature of physical laws. The speed of light remains constant, the background temperature of the universe stays stable, and physical rules remain solid. Only space keeps expanding, creating vast empty regions between galaxies, like a balloon being continuously inflated, growing larger and larger, but never thinning out. However, what's frightening is that we have no idea what dark energy really is. It doesn't emit light, doesn't interact with matter in conventional ways, and is nearly invisible to all observational tools. For this reason, the nature of dark energy is considered one of the greatest mysteries in cosmology. If humanity cannot understand it, then it also means we'll forever stand before the locked door of the universe, with a key that never exists. The number 93 billion light-years sounds truly enormous compared to the universe's age of 13.8 billion years. But strangely, it's completely logical, because throughout that time, space has continuously expanded under the influence of matter, radiation, and dark energy, all following the laws of general relativity. What scientists have determined is this: the observable universe, that is, the part where light has had time to reach Earth since the universe formed, has a diameter of about 93 billion light-years. But what's interesting is that Earth is not at its center. Every position in the universe, if observed from there, would see a similar observable universe as we do. Therefore, the question, how vast is the universe really, may no longer be that important. Because that 93 billion light-year limit isn't a real boundary, but only the limit of our ability to see, a curtain of light that we, at least for now, cannot pass through.